Welcome physics students. I have a challenging problem for you to have a go at today. Consider a ball that is initially stationary and it's allowed to fall, and in doing so it covers a displacement. I want to know the displacement of this ball given that it travels the final quarter of its journey in only 1 second. So here's a pictorial representation situation. We have a ball that's dropping, accelerating due to gravity, and it covers a distance h, and I've just labelled that with a capital H. We're breaking this into two sections. We have the bottom quarter of the journey, which means it travels h over 4, 1/4 of the distance, which means on the top we have 3/4 of the distance, 3/4 of h, or 3h on 4. That's our breakdown to try and solve this problem. The only other information we're given is that it starts stationary and it takes 1 second to cover the final quarter of its journey. Let's now break this into sections visually, which we'll refer to for the rest of this calculation. So we've got two sections. Section A, the top 3/4 of the journey in terms of distance, and Section B, the bottom quarter of the journey in terms of distance. Recalling that we're trying to determine the total distance of this ball's drop, given that its final quarter of displacement occurs in 1 second. Let's use some SUVAT variables to map out this information. So here we have it. Section A, and I must state that because the ball is moving downwards, we're going to take everything moving downwards as a positive value. So we have initial velocity of 0, acceleration due to gravity in the same direction as the falling ball will be positive, so it's positive 10 meters per second. The displacement it travels will be 3/4 of the total height that we're trying to calculate. Now, interesting enough, we don't know the value of v when it reaches the end of section A. However, we do know that the final velocity at the end of section A becomes the initial velocity for the start of section B. So I'm going to call that v with a different colour. In fact, I'll call it v1. So once again, the ball starts with an initial velocity of 0, it accelerates downwards at 10 meters per second. It covers a displacement of 3/4 of the total h, and at this point it has a velocity, a final velocity for section A of v1. Now let's consider section B. Okay, considering section B, what we have is still an acceleration of 10 meters per second. We were told it took 1 second for the ball to travel the final quarter of its displacement, so t equals 1. The displacement it's covering in section B is 1/4 of the total h, so h over 4. Now, the initial velocity, we don't physically know it, but we do know the initial velocity of section B will be equal to the final velocity of section A. These two velocities are equal and very important in terms of how we solve this problem. Now, using the SUVAT equations for section A, we can put these 1, 2, 3, 4 variables into one mathematical expression. And it is as follows. We can now further simplify this expression. And again, we can simplify this further. And finally, we get okay, let's examine this. v squared equals u squared plus 2as. We sub in our values where v is this final velocity v1 for section A. We go all the way through this. We simplify our right hand side. 2 tens is 20, 20 times 3 is 60, 60 divided by 4 is 15. I then re-express this, making h the subject. h equals v1 squared over 15. That's equation 1 that we've found from section A. Let's now examine section B, where we have a u, a, t and an s. There'll be a SUVAT equation that uses these 4 variables. We'll enter that data in, and we'll create a second equation where h is the subject. So here's our variables, and here's our appropriate equation, using the s, the u's, the t's and the a's. Let's now sub those values in. Let's now simplify this by multiplying both sides by 4. And there we have it. We now have for section A a mathematical expression using h. And we now have for section B a mathematical expression for h. If the two h's are equal, that means the left-hand sides of equation 1 and 2 are equal, so the right-hand sides must also be equal. So we're going to equate the right-hand side of equation 1 to the right-hand side of equation 2. This gives us the following expression. Now to simplify this, let's multiply both sides by 15. So 15 times 4 gives me 60, 15 times 20 gives me 300. This expression looks like a quadratic. It's got a v1 squared and a v1 term. Let's make this look like a typical quadratic equation. And there we have it. We now have an expression just in terms of v1s. We can now go ahead and solve this to find out what v1 is and then substitute it back into this expression or this expression to find h. To do this, we'll have to approach this as a quadratic equation. So here's our quadratic equation. v1 squared take away 60v1, take 300 equals 0. We want to calculate what is v1. We've got a v1 squared term and a v1. This is a typical quadratic equation. Now to solve this, we use this equation. This uses references of values or coefficients a, b and c. Let's highlight those. A v1 squared is the same as having 1 out the front, 1 v1 squared. It makes our terms a lot easier to understand. So our coefficient a is represented by the number 1. Our coefficient b is represented by the negative 60. And our coefficient c is represented by negative 300. Well, a is a coefficient on the v squared, b is a coefficient on the b, and c is the other numerical remaining coefficient. So here a is plus 1, b is minus 60, and c is minus 300. We can take those values, put it into this equation, and that will give us our answer for v. So let's give that a go. So here's the first stage, subbing in all our coefficients a, b and c into our quadratic equation. Negative b, and b was minus 60, plus or minus b squared, negative 60 squared, take away 4 times a times c, which was negative 300, all divided by 2 times a, which was 1. Let's now simplify that. Okay, the two negatives make this a positive 60. Negative 60 squared gives me 3,600. 4 times 300 gives me 1,200, and the two negatives give me a positive. And I'm dividing that by 2. Let's simplify further. Let's now simplify this even further. Now from this position, we can have two possible solutions. One is at 60 plus 69.3 over 2, and the other is 60 take 69.3 over 2. Let's look at both these options. Let's continue this calculation to find the two possible values for v1. So we've got two options for our velocity v1. Either v1 is equal to 64.6 meters per second, rounded, or v1 is equal to negative 4.65 meters per second, rounded. We can't have a negative velocity. The ball isn't accelerating downwards and suddenly going upwards. So this calculation has proven velocity v1 at the end of section 1 and at the start of section b will be 64.6 meters per second. Let's now substitute that back into our earlier equation, equation 1, to find out what h is equal to. Earlier in this video we discovered that h equals v1 squared over 15, equation 1, and we also discovered that h was equal to 4v1 plus 20, equation 2. Just a minute ago we also found that v1 was equal to 64.6 meters per second, and we're going to call that equation 3. Now we can substitute that value for v1 into equation 1 or into equation 2 to find the final answer of what height this ball has fallen, such that its final quarter of distance is covered in 1 second. So let's solve that now. First of all, let's consider equation 1. So substituting our value for v1 of 64.6 meters per second into equation 1 gives us a height, h, of 278.2 meters. Let's back that up by considering equation 2. So let's now substitute the value of v1 into equation 2. Once again, we get the same answer, give or take a little bit due to rounding. Equation 2, when I substitute in the value for V1, results in h, the total height of this ball dropping, of 278.4 metres. Either we substitute V1 into equation 1 or equation 2. Regardless, we get an answer of 278 metres.
You've been watching a Juddy Productions video. If you've enjoyed and indeed learnt something from this video, then please remember to like, share, comment and subscribe. And as always, thanks for watching.